Okay, so this is the sample problem that we had started. On this one, we're going to try to find the percent of composition of each of the substances. I think it's just a little slow in responding, I guess, today. Okay, so copper 1 sulfide, they give us the formula up there. And remember the method that I told you that I like to use when I'm doing these is I write down the formula, which in this case is Cu2S, and then I list the elements and down the side, and then I write down how many atoms I have of each. I have 2 carbon atoms and 1 sulfide atom, copper atoms, sorry. And then I look up on my periodic table, so you're going to need your periodic table to do this. And I'm going to look up copper, which is element number 29, and I have 63.55 is the average atomic mass for copper. And then I look up sulfur, which is 32.065, that would round off to 32.07. That next one, it's an even number. I guess actually technically it's 6 according to our rule, right? If it's even, we don't round up because the next number is 5. If it had been odd, we'd round up to the next even one. Okay, so that's what we'll use for this one. And then this is going to be 32.06. This one here is going to be, let's see, 0, 1, 10. Is that right? One? Yeah, we'll see what they have up here. 127.10. There we go. Okay, and then I'll add them up, and I get my 159.16 is what we're going to use here. They have 59.12. We're going to do this. Now remember that technically this is atomic mass units, because we're just talking about one formula unit. If it was a whole mole, this is one formula unit, just to remind us of that. One formula unit has this mass. If I have 6.02 times 10 to the 23rd formula units, that's Avogadro's number up there. Then if I have 1 mole, which is 6.02 times 10 to the 23rd formula units, then it's the same number, 159.16, but now it's in grams. It's that many grams per mole. So this is my method. That's the book's method. You can pick which method you like better when we're doing that. Okay, so do we have any questions so far? Yes.
So if you get the one formula unit, is that basically going to be your answer? It's just in a different unit?
Yeah, it just, like, if they ask you what's the formula mass, then you would just write down this. If they wanted the mass of 1 mole, then you would write down it in this version. Numbers are going to be the same. It's just that the units would be a little bit different, right? Okay, so far, we haven't done the percent of composition yet. We've just gotten the pieces that we need. Okay? Now, to figure out the percent of each, I'm going to take their part, divided by the whole. Okay? This is the part that copper is causing. This is the part that sulfur is causing. and this is their combined mass. This is the whole. Okay? So to find out the percent of copper, I'm going to take 127.10 divided by the whole, which is 159.16. You could put whatever units you want here, but they would cancel, right? What's on top would be the same units as the bottom. So I'm going to leave them off here, and then you're going to take it times 100, and then you'll have your percent. For the sulfur one, the part that's sulfur is 32.06. I'm going to divide it by the whole of the whole formula mass. And I would have its percent. So there's the, okay, and so the first one's going to give us a percent of 79.85%.
Hey, that adds up to 100.
Say what?
That adds up to 100.
It should come very close if it doesn't. Okay, and it should add up to 100. But here's where I want to just kind of, I don't know if I'd say forewarn you, but prepare you. When you do it, you know, we've probably been rounding some numbers here. So when you do it, you might, when you add it up, you could end up with like 99.99% or 99.98% or something like that, or might even go over 100. You know, be 100.01 or 100.02. Okay, that's just because of our rounding. We caused that. It doesn't mean that you did it wrong. It just the rounding affected my final. So I have to find out what the parts are and the whole, and I do that by just finding out the molar mass, and then I take each part divided by the whole, and I get my percentages. Okay, so it isn't really. I don't think it's that difficult, is it? Think you can do that? Okay, so as Davis said, you know, it should add up to 100. That's your check to see if you've done it correctly. Now, if you end up with like 89.10 or something like that as when I added them up, that means at least one of them's wrong.
If you get like 120.
Yeah, that would probably be bad too. So that you did one of them wrong, probably over here. Now, if you did something wrong over here, you could still have it add up to 100, but you just still have a whole bunch of wrong answers. You know, so how well this turns out is predicated on how well this is, how correctly you did that. Okay, now here's one more that is a little more, it's like an element more difficult, because we're adding one more thing to the formula that you're not familiar with, okay? Okay, it says, as some salts crystallize from water, they bind water molecules inside the crystal. When you touch the crystal, it'll still feel dry, but actually inside the crystal is hidden water molecules. They're incorporated into the crystal. Sodium carbonate forms a hydrate in which 10 water molecules are present for every formula unit of sodium carbonate. Now, so that means when I write this formula, I'm going to write the formula for sodium carbonate, which is N2CO3. And then, do you see the little raised dot in between? We often in science use raised dots in between two things, not to mean multiply, but to kind of mean attached to, or like plus. Okay? We don't want to write plus because that would confuse us later on when we're writing chemical reactions, because we always put plus in between the things that are reacting, or plus in between the things that are produced. So, but that is a little raised dot that means it's part of the formula. And it says that that whole thing has a molar mass of 286.19. Now, before we go on, I want to make sure that you understand how you would go about doing that, okay? Or how you would get the 286.19. If I covered up the 10 waters, if I just erase that out of there, would you know how to find out the molar mass of Na2CO3? Okay, that's just like we've been doing, right? So then, all that's left to do is I find the weight of water, and then how many waters are up here? 10. So I take the weight of water times 10, and then add it to my first answer. That makes sense or not? So I find the molar mass of water, H2O, but it's not just one H2O, there's 10 of them. So I'd have to multiply it by 10. And then add it to the molar mass of sodium carbonate. Okay, there's a chemical molar mass of that, okay? Now, 1 mole of that contains 10 moles of water. Does that make sense? For every 1 N2CO3, I have 10 waters. So if I have 1 mole of that whole thing, that means I have 10 moles of water. And the molar mass of water is H2O. How do you think they got that?
Well, they took 2 masses of hydrogen times 1 mass of oxygen.
Only one word wrong. Plus the mass of oxygen. You said times. Okay. Okay. Otherwise, exactly right. Okay. So you had the mass of 2 hydrogens plus the mass of 1 oxygen is 18O2. Okay. 10 moles of that is going to be 180.2 grams of water, right? And if one of them is 18.02, 10 of them would be 180.2. Okay, and they wanted us to find out what part of that, what percent of that crystal is water. Okay, so I'm going to take the part. That 180.2 is the part that's water. The 286.19 is the mass of the sodium carbonate with water in its crystal. It's the whole thing. That's the whole. Okay? This little square right here is supposed to be a dot, that raised dot. Sometimes it does it, sometimes it doesn't. I need to go back and fix it sometime because I'm on a different computer here. So I'm just taking the part divided by the whole. So percents are always part divided by whole. So all you have to do is identify what's the part, and then what's the whole, and you divide one by the other, and you have the percent. So in other words, in that crystal, over almost 2/3 of that crystal is actually water. So well, and here's one thing that you don't know, but you may not know, let's say it that way, is if I took that a piece of this rock, sodium carbonate, and I would put it in an oven at a temperature above the boiling point of water, all the water would evaporate out of the crystal, and it would be lighter, wouldn't it? It would only have a mass of, what would that be? About 37% of what it did before. It'd be a lot lighter. So heating it will cause the water to evaporate and leave the crystal. Anhydrous is the word that we call it. Anhydrous. An means not, right? So it means without water. But if I would allow that to sit over time, because that crystal is missing its water molecules, it will take water out of the air and put it back in the crystal, and eventually that crystal would be all the way back the way it was before. So it's not a permanent thing when you heat it. Well, that's it. So that takes us to the end of that section. So you have the remainder of the period to work on that. You what? Oh, you already printed one off? Hey, you're ahead of me. And you did too. That's good. I'm okay with that. You may, and Landon, you can go sit back with Jake now. Unless you don't want to anymore. It passed.
Would anyone agree just
Oh, I need to turn this on.